Alright, so we have an inclined plane problem. We've got a mass that's 10 kilograms sitting on a slope that has an angle of 35 degrees. We want to figure out, well, what is the net force acting on the mass? It's frictionless, so it's going to move. We want to know, we're going to assume it's moving down this way. But we need to figure out how to calculate the acceleration. Remember that an object will always accelerate in the direction of the net force. I'm not saying it moves in the direction of the net force, but it always accelerates in the direction of the net force. So, looking at this, I need to figure out what vectors I'm going to put in to get the ball rolling. So, it's got mass, it's got weight. So, weight's going to be my component that I'm going to, or force that I'm going to put in first. I can easily calculate that. This is 10. We're going to say G, for the sake of this, is 10. So this is 100 newtons. Because this is at an angle to this surface, it's not straight up and down against the surface, I'm going to have to break the weight into components, the X component and the Y component. So I'm going to create my little box. I'm going to say this going this direction is my perpendicular force, and this going this direction is parallel. It's parallel to this surface, so it's really this one. When you sort of visualize what's going on, that's really your F parallel. This 35 degrees is this interior angle, right? We've shown that in class, so I'm going to label that. So this is 35 degrees. And I'm going to find all the other forces acting. Now, what I also didn't draw, and I'm going to put in, is that our normal force should counterbalance this perpendicular force. So this is our normal force. These are equal in magnitude, opposite in direction. I know they're equal in magnitude because the box isn't sinking into the inclined plane. It's not levitating and rising off the inclined plane, even though that would be cool. It's not doing that. These are balanced, right? These are equal. So this is less important for me to find, but I'm going to go ahead and we can go ahead and calculate that anyway. So we need to figure out our net force based on all these components of our gravity. So my parallel force is opposite my angle, so I'll write that in. This is our opposite side. Our weight is our hypotenuse. It's opposite this right angle, but it's also the longest side. And this is our adjacent side. So we're looking at some SOHCAHTOA stuff coming our way. So if this is opposite, this is hypotenuse. I don't know this number, so that's not really useful to me. This is an unknown. It doesn't matter which one I start with first, but this is unknown. I do know the hypotenuse. I have theta, hypotenuse, and opposite. O, H, and then the angle. So I'm going to look at using sine. So I say sine theta equals opposite over hypotenuse. So sine 35 degrees equals opposite, so F parallel over my hypotenuse, which is 100. I move that over to this side. So really my F parallel is my hypotenuse, 100 newtons, sine of 35. So F parallel is .36 is what I'll round it to. 57.36. Okay. Let's go ahead and look at the perpendicular just to make sure we know how to solve for that. So this is the adjacent side, this is an unknown, this is our hypotenuse, this is our angle. Now we know the parallel force, we know the opposite, so we could do tangent opposite over adjacent. We'll go ahead and use our hypotenuse, that's the way I'm going to do it, but you could do it the other way. So this is looking at cosine of that angle. So we're going to say cosine theta equals adjacent over hypotenuse. Say cosine 35 degrees equals the perpendicular force divided by 100. So move that to the side. 100 newtons cosine 35 equals perpendicular force. So cosine 35 times 100. So this is equal to 81.9 newtons. Okay. So we still haven't found our net force, but we have found different components of it. So we know that this value is 81.9. This value is 81.9. Right, 81.9, 81.9, this is 57.36. We're not really using this anymore, right? We've already broken it down into components, so it doesn't count in our net force. We've already broken it into X and Y components, right? So, looking at this then, if this cancels with this has already been broken down into components, so we don't use that. The only component of our net force is really our F parallel. We've talked about that in class already. So our net force is equal to F parallel only when there is no friction. Okay, so we've solved F net. F net is that number. Now we want to figure out how the object's going to accelerate. So we can say, I'll use a different color. So we say A equals F net, which is really our F parallel over the mass of the object. So we have our 57.36 kilograms is meter per second squared over our mass, which is 10. Kilogram cancels, so I'm going to accelerate 5.736 meters per second squared down the ramp. So I have all the information completed and solved for this inclined plane problem.